Right here we have a cylindrical tank and water is entering it through two pipes. So there's water coming in here with a volumetric flow rate of Q1, water coming in here with a volumetric flow rate of Q2, and the level of the tank, the level of the water in the tank remains constant. And we're asked to find the average velocity of the flow leaving the tank through the pipe with an area A3. So this should be a V bar 3. That's the average velocity leaving the tank. So this is going to be a conservation of mass problem. I'm going to draw a control volume that surrounds the water inside the tank. And I'll apply conservation of mass to that. So the time rate of change of mass inside the control volume will equal the rate at which mass is coming in minus the rate at which mass is going out. And so first of all, let's talk about the time rate of change of mass inside the control volume. Since the height is not changing and the area is not changing, the volume of water in here is not changing, and of course the density of the water is not changing. We're assuming an incompressible substance for the water. So that means the mass isn't changing. So there is no change in the mass within this control volume. We do have mass coming in over here, and the mass going out, but the total quantity of mass inside that control volume remains constant. So that's time rate of change of mass inside the control volume is 0. Now as far as the mass flow rate coming in, we have mass coming in two spots, here and here. And these are volumetric flow rates, so it's the volume per unit time. Like it would be like cubic meters per second, for example. So to get a mass flow rate, we would multiply those by the density of water. So it'd be the density of water times Q1 plus the density of water times Q2 for the mass flow rates coming in. And as far as the mass flow rate going out, that would be equal to the density of the water times the average velocity where it's going out times the area through which it's flowing. So that's how you calculate a mass flow rate, just a density times the average velocity perpendicular to the pipe times the cross-sectional area of the pipe, A3. So let me just go ahead and write this all out a little more clearly. We're trying to find the average velocity, V3, so we can just go ahead and rearrange this equation. You'll see the densities cancel out. We're assuming the water's incompressible. So V3 bar, the average velocity, would be Q1 plus Q2 divided by A3. So that's just a straightforward application of conservation of mass.